Dear students, welcome to my new channel RX by Jahid. Today we will learn about gastrointestinal absorption of drugs under the course of biopharmaceutics and pharmacokinetics. So let's start. Drugs that have to enter the systemic circulation can be administered by three majority ways. So there are three main ways for drug absorption. One is enteral route, another is parenteral route, and another is topical route. Enteral route includes paroral, gastrointestinal, sublingual, and rectal routes. Parenteral routes includes all routes of administration through or under one or more layer of skin, and topical routes include skin, eyes, or other specific membranes. This is the overview of the entire absorption process. This is the overall GI lumen, and this is the cells of the GI lumen, that is enterocyte. So whenever we're taking any solid doses from like tablet or capsule, it is getting disintegrated, and after that the granules are deaggregate to form fine particles. However, whatever the solid doses from granules or fine particle is, it will ultimately result in the drug in solution. That is, it will be in form of solution. Okay, so that solution would then be ready for absorption. So we can see that unbound unionized drug will get absorbed into the enterocyte, and from the enterocyte it will come into blood. So this is the GI lumen, this is the enterocyte cells, and this is the blood. Then it will again come into the blood. So this is the overall absorption process. There are three basic mechanisms for drug absorption. These are transcellular or intercellular transport, paracellular or intercellular transport, and another is vesicular transport. So we can see that in case of transcellular, trans means through something. So through the cell, the transport through the cell is called transcellular transport, and paracellular means between the cell. Transport between the cell is called paracellular transport. However, sometimes drug can be transported via phagocytosis or from the form in form of vesicle. Okay, so this is called vesicular transport. We'll discuss about this in our next slides. So the first absorption process is transcellular transport. So there are three steps involved in the transcellular transport of drugs include, first of all, they will be permeated through GI cell membrane. That is the major obstacle to drug absorption. After that, it will move across the intracellular space. And after that, it will permeate through the basolateral membrane that is of secondary importance. However, it can be divided into two transport process again, and one is active and another is passive transport. Here we can have a general idea about this transport system by looking at their comparison. As we have already understood that active transport is the transport which requires ATP, but in case of passive, it doesn't require any ATP. So the passive transport usually follows fixed law of diffusion. We'll discuss this later. That is, it moves along gradient, but in case of active transport, it moves against gradient. That is from lower concentration to higher concentration, but the passive transport occurs from higher to lower concentration. So the transport proteins are optional, but in case of active transport, these are required because this will require ATP, and ATP will be provided by any enzyme or carrier or protein. Usually, oxygen, carbon dioxide, water are passively diffused, and usually ions are actively transported into the blood. This speed is faster because no energy is required, but this is slow because energy is needed, and it also require protein for better transport. It's less regulated, but it is highly regulated because energy is required, and if energy is utilized, then active transport can be happened. So in case of cellular roles, we can have gaseous exchange or waste removal are example of passive transport, and in case of nutrients uptake or ion balance, we see the importance or role of active transport. So this is independent of cellular energy. It has been discussed earlier, but it is dependent on energy level. It is generally less specific, but it is highly specific for transported substance. So let's dive into passive transport process. These transport processes do not require energy other than that of molecular motion to pass through the lipid bilayer. However, it has been classified into four transport systems. One is passive diffusion, another is pore transport, number three is ion pair transport, and the last one is facilitated or mediated diffusion. So let's discuss this. So passive diffusion, which is also called non-ionic diffusion, also called concentration or electrochemical gradient. So most drug cross biological membrane by passive diffusion. It's seen that nearly more than 90% of the drug are passed by this mechanism. It is defined as the difference in the drug concentration on either side of the membrane. Diffusion occurs when the drug concentration on one side of the membrane is higher than that of other side. The process is passive because no external energy is required. The driving force for passive diffusion is the difference in the drug concentration on either side of the cell membrane. During passive diffusion, the drug present in the aqueous solution of the absorption site partitions and dissolves in the lipid material of the membrane and finally leaves it by dissolving again in an aqueous medium, this time at the inside of the membrane. However, most important thing is that passive diffusion is best expressed by Fick's first law of diffusion. This is very important, which states that the drug molecule diffuses from a region of the higher concentration to one of the lower concentration until equilibrium is attained, and that the rate of diffusion is directly proportional to the concentration gradient. So let's see the equation, then we can easily understand. This is the Fick's first law of diffusion equation. We can say this is the diffusion rate, D is the diffusion coefficient, we know A is the surface area, K is the partition coefficient. It is the more lipophilic, the more would be the diffusion. This is the concentration gradient. The concentration in the GIT. This means the concentration in the blood. Okay, there should have a gradient all of the time. So these are all proportional to the diffusion rate. Higher would be the diffusion coefficient, then this will ultimately increase the diffusion. Then if you increase surface area, then this will ultimately increase diffusion. Lipophilicity will increase the diffusion. Then the more concentration difference, the more diffusion would be. But this is directly not directly proportional to thickness of the membrane, that is H, because you see, if you increase the thickness of the membrane, then it will be very difficult for have a better diffusion. So that's why H is inversely proportional to this. As more than 90% of the drug are passed through this passive diffusion process, so we have to learn descriptively about this. So let's start. These are the certain characteristics of passive diffusion process. So drug moves down the concentration gradient, indicating downhill transport. That is, drug is moving from higher to lower concentration. Okay, so the more difference, the more would be the diffusion. The next one is the process is energy independent and non-saturable. So why energy independent? Because it requires no energy, and not saturable because it's not requiring any enzyme. Okay, if it requires any enzyme, then it would be saturable and it would be following Michaelis-Menten equation that we have learned in biochemistry. Okay, so it's not depending on all of this. So that's why it is energy independent and non-saturable. The rate of the drug transfer is directly proportional to the concentration gradient between GF fluid and the blood compartment that we have already discussed. The greater the area, lesser the thickness of the membrane, faster the diffusion. So it can be seen from the equation. Thus, more rapid is the rate of drug absorption from the intestine than from the stomach. Okay, because Intestine have a greater surface area. We know the villi, the microvilli increases the surface area of intestine. That's why drugs are mostly absorbed from the intestine. The process is rapid over short distances and slower over long distances. Equilibrium is attained when the concentration on either side of the membrane become equal. You know, if the concentration gradient is zero, that is, if concentration in GIT and concentration in the blood becomes equal, then these will ultimately stop our diffusion. Drug which can exist in both ionized and ionized form approach equilibrium primarily by the transfer of an ionized species. The rate of transfer of unionized species is 3 to 4 times the rate of the ionized drug. That is, we have already learned that if it is unionized, then it would be very neutral and lipophilic in nature. So this will ultimately increase the diffusion of the drug. Okay, so unionized drug would be absorbed better and faster than that of ionized drug. So our next characteristics is the drug diffuses rapidly when the volume of the GI fluid is low. Conversely, dilution of the GI fluid increases the drug concentration in these fluids. Okay, we can easily understand that if the concentration is equal to mass by volume. Okay, so if you increase the volume, then what would ultimately happen? Concentration would be decreased. So if concentration is decreased, then ultimately our diffusion would be decreased. So this has been said here. This phenomenon is however made use of in treating case of oral overdose or poisoning. So our GI fluid volume has an impact on the diffusion of drug. Okay, because GI fluid volume will ultimately change the concentration, and these will ultimately change the diffusion. So greater the permission or water partition coefficient of the drug, that is lipophilicity of the drug, faster the absorption. You can see from here that is directly proportional. Since the membrane is lipoidal in nature, a lipophilic drug diffuses at a faster rate by solubilizing in the lipid layer of the membrane. The process is dependent to a lesser extent on the square root of the molecular size of the drug. Drug having molecular weight between 100 to 400 Dalton are effectively absorbed passively. The diffusion generally decreases with the increase in the molecular weight of the compound. However, there are exceptions. For example, cyclosporine, a peptide of molecular weight of 1200 is absorbed orally much better than any other peptide. So we'll discuss this later. Our next passive transport process is ion pair formation. So strong electrolyte drugs are highly ionized or charged molecules such as quaternary nitrogen compounds. These drugs penetrate membrane poorly when linked up with an oppositely charged ion. An ion pair is formed in which the overall charge of the pair is neutral. These neutral complexes diffuses more easily across the membrane. So the formation of an ion pair of propranolol, this is a basic drug. There is a positive charged ion drug. So it has been shown that this is propranolol, that is basic drug. Basic drug means it contains nitrogen. So if it contains nitrogen, then it would be positive. So the positive would be polar. Okay, it's a polar drug. So it would be difficult to pass through passive diffusion. So decrease or neutralize its polarity. If we add this with another endogenous anion, then what would happen? It would be neutralized. So this is a neutral ion pair complex. Then as it is neutral, then its polarity has decreased, and which is suitable for passive diffusion, then it will have a passive diffusion and get into the blood. After going to the blood, these will again dissociate it to form the free drug. Okay, so this is ion pair formation mechanism. The next one is port or convective transport. A certain type of protein called transport protein may form an open channel across the lipid membrane of the cell. Very small molecules such as urea, water, and sugar are able to rapidly cross the cell membrane through these ports. And last one is carrier mediated transport. We can see here that If it is passive diffusion, then it's directly proportional to the concentration. But in case of carrier mediated, that is enzyme dependent, you can see that at one point it is getting saturated because it's enzyme dependent. So carrier mediated transport has been shown here. This is a carrier. This is vitamin B12, which has a high molecular structure, molecular weight. Then this is an intrinsic factor which help in the binding of the drug with the carrier. So after that, a complex is formed, which would ultimately get into the blood, and after coming into the blood, it will dissociate. So this is a carrier mediated because the carrier is helping the transport of this vitamin. Okay, and this is also called facilitated diffusion because it's also diffusion, but it is facilitated. Why facilitated? Because carrier is helping. This carrier is nothing but a protein or enzyme. So that's why this is called carrier mediated transport. So our next topic is active transport system. Active transport is more important process than facilitated diffusion in the absorption of nutrients and drug. So these properties would be just opposite to passive diffusion. Let's say the drug is transported from a region to lower to one of the higher concentration. So against the concentration gradient. So in case of passive diffusion, we have seen that it was through the concentration gradient, but it is against the concentration gradient. The process is faster than the passive diffusion. Since the process is uphill, energy is required in the work done by carrier. As the process requires expenditure of energy, it can be inhibited by metabolic poisons that interfere with the energy production like fluorides, cyanides, dinitrophenol, and lack of oxygen. Endogenous substances that are transported actively include sodium, potassium, calcium, iron, glucose, amino acid, vitamins, etc. Usually ions, vitamins are transported by this mechanism. So these include the drug which are having structural similarity to such agents or proteins are absorbed actively, particularly the agents used in the cancer chemotherapy. For example, 5-fluorouracil, an anti-cancer drug, and 5-bromouracil transported via pyrimidine transport system. So this is the protein or the enzyme system, and this is the drug. So these are passing through this system. So absorption of methyl dopa and levodopa, these are drug for Parkinson disease. So these are transported via L-amino acid transport system. So ACE inhibitor like enalapril transported via peptide carrier system. So this is the carrier system, and these are the drugs. So this is the overall overview of active transport system, that energy is utilized, ATP is utilized in this case. Our next topic is paracellular or intercellular transport. So there are basically three transport mechanism, that is transcellular, paracellular, and last one was vesicular. So we'll discuss now about the paracellular transport. So paracellular defined as the transport of drugs through the junction between the GI epithelial cells. This pathway is of minor importance in drug absorption because most of the drug are passed through passive diffusion. Two paracellular transport mechanisms involved in drug absorption. One is permeation through tight junction of the epithelial cell. It occurs through the opening which are little bigger than the aqueous pores. Compounds such as insulin and cardiac glycoside are taking up this mechanism. Another one is persorption, that is permeation of the drug through temporary openings formed by the shedding of two neighboring epithelial cells into the lumen. So our last topic was vesicular transport. So we can see that a macromolecule is engulfed by our cell, then it is passing through the cell and comes into the blood. It is as like as phagocytosis that we have learned before. So it is the process of engulfing particle or dissolved material by cell. Pinocytosis and phagocytosis are forms of vesicular transport that differ by the type of material ingested. So what is pinocytosis? It refers to the engulfment of small molecule or fluid. And what is phagocytosis? It refers to the engulfment of large particle or macromolecule. Okay. So some drugs can be transported by this mechanism, like vesicular transport is the proposed process for the absorption of vitamin A, D, E, K, and peptide in newborns. So these are the overall absorption process in our body. So in the next video, we'll learn about biopharmaceutical considerations in dosage form design. Thank you, everyone.